So now we are looking at the idea of equilibrium. Equilibrium, we happen to see rotational equilibrium few videos back. Here we are not only seeing equilibrium in rotation but also translation. So basically our object is in all aspect is in equilibrium. So we again are looking at rigid bodies. So please go back and look at the definition of rigid bodies. So that's important. So the basic idea over here is that a body, if it's at rest or in uniform motion, all forces acting on it will be balanced. It can be that there is translational forces, that is something trying to change its velocity. There's a counter force for that. Something is trying to rotate, there's a counter force for that. A rigid body is in equilibrium when it experiences no net linear or angular acceleration. This is achieved through balanced external force and torques. Now, condition for equilibrium, we have two main conditions, translation and rotational. So translation happens when we have vector sum of all the external forces on the body is 0. This ensures no change in linear velocity. Okay, so I can take an example, a rod basically. So I have a rod and I'm at one end, I'm pulling it, and the other end also I'm pulling it. So if this is 10 Newton, this also is 10 Newton. So this is your translation equilibrium. So it can be other side also, but they have to be in the same straight line. They have to be in the same straight line. They need not be in the middle. They can be anywhere actually. But yeah, I'm talking about translation only. So I need to talk about lines which connects the center of mass. So 12 Newton. And this is again a force with 12 Newton. Next, we need to have what? Rotational equilibrium. That is your translation equilibrium. The sum of all the forces on the x direction and the y direction, it will be 0. So even this can also be something like if I apply a force, no, it may not do that. Next is rotational equilibrium. The net torque about any fixed axis or point is 0. So there is this prevents from angular acceleration. Torque is calculated as a force times the perpendicular distance from the pivot point. So this point you guys already know. So these two conditions apply to, it can not only apply to something which is at rest, but also can apply to something which is moving at constant velocity. So this condition for equilibrium, if something is moving, does not mean that they are not in equilibrium. If something is moving and rotating, does not mean it's not in equilibrium. They can be in equilibrium even if it's moving and rotating. But it has to be with constant angular displacement and constant linear displacement. That is your condition. Okay, so that's an important note. So you can get MCQs out of this point, So types of mechanical equilibrium. Mechanical equilibrium can be classified into 3 types based on the system's response to small disturbance. These depends on the potential energy landscape, stable at minima, unstable at maxima, and neutral on flat region. This classification applies to rigid bodies like beam, pendulum, or vehicles. So the list is stable equilibrium, unstable equilibrium, and neutral equilibrium. Okay, so we'll learn about this in detail. So for now, we just got introduced to the idea of equilibrium, which combines not only rotational equilibrium, but also translational equilibrium. So rotational equilibrium, I didn't show an example. So this is mainly to do with translation equilibrium. For rotation, say I have, this is the center of mass and stuff. So if I hit a force, if I apply a force over here, say 14 Newton, at the same time I apply a force over here, 14 Newton. This tries to make it go round. That is, this is clockwise. This tries to make it go counterclockwise. Okay, so let me take it down. So these are your examples for your translational, and this is for rotational equilibrium. Of course, we have combination. It's not only that an object has to be either of one. So in this topic deals with equilibrium in all the cases. So we can have equilibrium not only that we're getting pulled from both the ends. So that's supposed to be straight set of straight lines. Also that you have forces. Say somewhere over here is 2 Newton, and no, like say 12 Newton, and somewhere over here double the length from your center is 6 Newton. So, the other way around. This is 6 Newton. If this length is x, this length is 2x. So basically we're looking at torque, right? So torque will counter each other and they will be 0. So this is the example of combined. This is in a combined version. So all this you have to be open to different things. So what I'm trying to tell is whatever we just tell, whatever the teacher tells, it's just a small part of a big picture. You should, as in when you do numericals, as in when you read questions, as in when you read theory, your mind should open up to all the possibilities. Don't constrain yourself. These are just general ideas. There are many possibilities, and showing all of them is highly impractical. So yeah, be open to different scenarios is what I suggest. Okay, now you guys have to see what interests you and you can write it. And by the way, we are studying about this 3 in the next video.